Hi, this is an add-on to section 13.3. We want to do a projection of a vector onto a vector and the dot product and get a little bit of more understanding about those things. So with the dot product, we have two vectors put together. We take the components of each and multiply respectively the first coordinates together and the second coordinates together. And then also we have a geometric interpretation, which is just the magnitude of the two vectors times the cosine of the angle in between. Note that this is a scalar. Then we also have this formula that we've been dealing with, the components of a force vector acting on an object. And so we have force parallel to the given vector. So this would be force parallel to the u vector. And this would be force perpendicular to the u vector. And so those are a couple formulas that we'll talk about as well. Okay, say for instance here that we want to project v onto u. So we write it like this, project v onto u. That's a v. And so that would be taking my vector v here, this one right here, and I want to project so it's like a light shining down this way onto u. So it's just going to be this segment right here. So now this is a vector, and we can tell that this is of unit length 3. So if we take the magnitude of that, the projection of v onto u, we're going to see that it's going to be equal to 3, okay? And the magnitude of u is going to be 6. So we have that information. What if we try the dot product? What if I do v dot u? As we should know is that we just take the respective x's, respective y's of those coordinates, multiply them together and add. And that would be the dot product. Well, what do we get for a total? Oh, this is 18. Okay, so now let's look back down here. We have a 6 and we have a 3. How does that relate to the 18? Sure enough that the projection of v onto u, and then the magnitude of that, times the magnitude of u is going to be equal to, the dot product. It's the same exact thing. In this case, it's 18. So really, what we're saying is that the length of our projection, which is this, times what we're projecting onto, if we multiply those two together, that would give us the dot product. So that's a different interpretation of what we see. So now the question is where do we get the 6 and where do we get the 3? Well, the 6 is pretty obvious because it is the magnitude of u, so that would be my 6. How do I get the 3? Well, we said it's projection. However, if we do look at this angle here, this is theta, how do we find this length right here? Well, I do know that this is a 3, 4, 5 triangle, so that's 5. So the question is, how do I get this 3 right here? Well, you can use trigonometry, and so I have the hypotenuse, and if I multiply by the cosine, 5 cosine theta, that should give me what my length of this piece is. And so this would be actually the magnitude and then the cosine of theta. Well, how do I get the cosine of theta? Cosine is going to be adjacent over hypotenuse, 5 times 3/5, so that would just give me my 3. So where do I get this 18? Well, there's the magnitude of u, there's the magnitude of v times the cosine of theta. Boom. There it is. So this is another way to represent the dot product. So in summary, what we've kind of just showed that this is the same thing as the projection of v onto u. And then take the magnitude. Same thing. Cool, right? Okay, we want to look at that other force formula that we do have there. So moving on with this formula, where does this come from and what are we trying to do? Well, this force, I want to find the components of it. So the component of this vector, and so I'm using v instead of f, but this, I just want the components of this vector. Well, that's going to be 3i, and then this would be 4j. I hope you can see that. We know that 3i plus 4j is going to be this vector right here. So I'm going to break it down in these pieces and try to figure out what the formula means from what we have. So if I look at the vector parallel for v, and that's the component of the parallel to u. So when we see this parallel, it means to u, or whatever we're projecting onto. So the v vector parallel, what I can do is, well, what is it? Well, it's just going to be 3i. That's our answer. Okay, so how do we get that? That's a little bit of a problem, but let's see how it goes. First of all, that vector does have to be in the same direction as u. So somehow I got to deal with u. And then the magnitude is going to be the magnitude of the projection. Well, from before we found out that that would be 3 times 6 if we did the dot product. However, I don't want to use 6 anymore. I want to find this 3. So it has to be in the direction of u, and I go 3 times it, and I want to get 3. Well, that's going to be a 1. I need a 1. So what does that mean for us? So instead of having u, I'm going to have the unit vector for u instead. And so what I can do with this is going to be equal to, where do I get the 3 from? Well, we get it from this right here, which is the same thing as the magnitude of the projection. So remember that this is a scalar. So when I do this, I can multiply this then by 1. That's what I really want to multiply by. So this thing that I'm going to multiply by has to have a value of 1. Well, what vector is in the direction of u that also has a magnitude of 1? Well, that's the unit vector. So I'm going to take that and divide by the magnitude of u, and then I'm going to use the magnitude again to get that 1. Well, if we look at this, this is just the dot product. So this is the same thing as v dotted with u that's been unitized. Now notice I'm missing one very key part to this. I'm not creating a vector yet. These are just scalars. So I still need the vector. Well, what I'm going to multiply by then is something in the direction of u. So I'm going to multiply by the unit vector of u in order to get that direction down for a vector's sake. And so going back down to here, I also need this. And this is where that formula comes from. So let's see what this means. I know that if I take this is 3 times the unit vector is going to be 1 plus 4 times 0, because the unit vector is just in the horizontal direction. And then if I multiply that by my unit vector is just going to be I plus 0j. And so when I do that, I'm going to end up with 3i. And so that's kind of where all this stuff comes from, right? I don't know if I'm making sense. I hope I am putting this together, but this is where all this formula comes from. So this is just a scalar, and then this would be the direction of it. Now if I know that v is equal to 3i plus 4j, and then v parallel is equal to 3i, how am I going to get v perpendicular? Well, v perpendicular would just be v minus v parallel. So it's 3i plus 4j. I got to put hats on, forgot. And then we're going to subtract off 3i. So this would just be equal to 4j. Okay? So that would be this formula right here. So that's all we're doing. So since my u was on the x-axis, these just turn out to be the components of my vector. So this is v parallel to u. So when we talk about parallel, it's parallel to whatever we're projecting onto. V perpendicular is going to be perpendicular to whatever we're projecting onto. So if I take this plus this, I'm going to get this. There you go. And so you can use that formula to find the other well, find this in the end. So the purpose of projecting onto the axes is to show you what happens when we don't project onto the axes. So now I'm going to project onto my u here, right here, which is not on the x-axis anymore. So I'm going to put v prime onto u prime. I'll probably just say v and u again, but I did this because this is a little bit different. For you people with linear algebra, that's how I got the rotation of this by 15 degrees. So it's the same exact diagram as before, but everything got rotated by 15 degrees. So now I'm going to project v onto u. And so this would be my resultant projection that I do have. The angle in between is still going to be theta, and then this is my projection. This one right here is going to be my v perpendicular, and then this would be my v parallel. Those are vectors. So now we want to try to find those. It's going to be a little bit different for us, but not too bad. But first of all, let's do the dot product and see what happens when we do the dot product between these two vectors. So this would be my B point, and then this would be my C point. And I carried this out to the full length on my calculator, no rounding, and I did get 18. Woo! Same thing. That's interesting. Or maybe not, because the length of this is still 3. The length of this is still 6. So 6 times 3 is going to give me my 18. So I'm hoping that you can see that this turns out to be identical to what we had before. It's just that we turn our head a little bit to get a new x-axis. So we're kind of having this as our x-axis. This is the angle measurement in between the two. And so even if I did the cosine formula for the dot product, it would still turn out to be the same. Everything's the same. So if I ask this question, I want a vector in the u direction with magnitude 3. How would we do that? Well, we monkey around a little bit, but we know that the magnitude of this thing right here is going to be 3. And I do know the magnitude of the unit vector in the u direction is going to be 1. So instead of using 6, I'm going to break that down into the unit vector, and I should be okay. So that's what we're going to do again. So I'm going to take my v, and then I'm going to dot it with the unit vector that I was just talking about. When I do that, I'm going to get a scalar, and that scalar will be 3. And what do I have to multiply by? Well, whatever's in the direction of the u vector. So a scalar times a vector is going to give me a vector that is in the direction of u. So then I got 3 times that vector that's in the direction of my u. That's not my unit vector though. So I got to divide this still by 6. So I took the 3, and then I took my coordinates of this point right here, and then I had to unitize that, and then I multiplied it all together, and I get this. Now, does this make sense? Well, let's try to plot it on the graph here. So I plot the point that corresponds to that. That's right about there. And voila. There is my vector, which is the F parallel. And in this case is V parallel. And then if I have my overall vector, this is going to be a lot of decimal places, so I'm just going to write it out and show you. So with all these decimal places, I get this as my perpendicular vector, which is going to be this one right here. Does it make sense? -1. That means that I'm actually going to go over here and be like right about here for my vector, which is the same vector as right there, which would be this vector right here now. And then this vector was my parallel, and then my v is here. So if I take the components, this plus this, that's going to add up to this right here. So those are the components of that v prime vector that we do have. Okay, I hope this sheds some light and makes this a little bit easier conceptually. I know there's a lot of stuff in there. The decimal places may have got you down, but really the main thing is that look at this as your x-axis. Turn your head a little bit, and we're projecting onto the x-axis. And then what's my angle in here? And then this is my v vector. I'm just finding the components of that. Okay, I hope this helped you. And let me know if you got questions. Take care. Thank you. Bye-bye.